Okay, all right, welcome to class, everybody. Okay, so happy Monday. As you may have noticed, we have a quiz at the start of next week. So if we go into that, there is a typo here. I guess, yeah, it's going to be open just like that. It'll be the same as our first quiz. It's on Brightspace. You do it whenever you want. It's open for a little over 2 days. It'll open on Monday morning, and it'll close at 6 a.m. on Wednesday. So this should say open until 6 a.m. on Wednesday, November 2nd. And the focus is everything that we've done since the last quiz. And that will actually include what we do today and what we do on Wednesday. But I'm going to try to keep those pretty high level. Like basically, do you understand for Wednesday, do you understand what a stack is? Do you understand what a queue is? Can you very high level understand what they would be used for? Not like the deep implementations that we've been working on for arrays and linked lists and stuff like that. But do know that that is fair game. Similar to the last quiz, you can use anything basically linked from the course or your own assignments, and you can open up Eclipse or whatever IDE you're using, and you can actually write and run Java code. So all of that is good. However, you can't ask anyone for help or Google anything. And yeah, again, it'll be a hard 1 hour cutoff to take the quiz. There should be a really short practice quiz already up just to kind of show you a flavor of the questions, but we'll go more deep. We'll cover that practice quiz on Friday, and then I'll also do more of a review for the quiz on Friday as well. Cool. Any questions on the quiz? Cool. So yeah, so that's coming up. And hopefully everybody got Project 3 in. And my hope is Project 3 will make, if you want to spend very little time on Lab 9, you can, because you've already practiced writing these experimental runtime tests. So hopefully a lot of that detail you already have practice with, but in Lab 9 you also have the option to not just copy the code that's given, but write your own algorithms, so you could take some more time with that if you want. Okay, so we are going to continue with big O notation, and then also, so originally on the schedule we had recursion for today, but I think that it's going to be better for us to cover recursion when we start doing algorithms as prep for algorithms like binary search and merge sort that actually are recursive algorithms, because we're not actually going to be studying any recursive algorithms until a little bit later in the course. So instead, we'll finish off today with a method that we use to prove the correctness of algorithms. So I assume, do you see this in 246? I just know. Have you seen loop invariance yet? Okay. No problem. So you probably will see loop invariance in 246, but we will cover them briefly today as well. Okay. So, big O notation. Yeah, we're going to go to some slides about this. So, if you remember, I think it was on Friday, we got into groups and we counted the number of primitive operations in this function, or in this method, and we came up with about, I think we said that there were 6n total primitive operations. So those were things like assignment, things like accessing fields, because fields are already pre-computed, things like making these comparisons, accessing a element of an array. All these are primitive operations, and we said there were 6n total primitive operations here. And our sort of goal is going to be able to say, well, that's pretty specific, like 6n, 5n, 20n plus 2, all of those are possible numbers of operations, but we want to make more general statements about runtimes that are that can be more characteristic of an algorithm overall. We also saw that these things actually really matter as our input sizes get large. And so the big idea here is that as these input sizes get large, what we really care about is the growth rate of the function as we make our input size bigger. So here we're looking at different functions on a log-log scale. So you'll notice that we're graphing these red lines are quadratic, but they don't look like quadratic functions, and that's because we're on a log-log scale, which really highlights the asymptotic behavior of our functions. And so we can see what this is showing is that even if we have quadratic functions that have these constant factors like 10 to the 5th or lower order terms like 10 to the 8th times n, they might have different behaviors for small inputs, but it's the large inputs where they really start behaving just like any other quadratic function. So this here is a quadratic function with lower order terms and constant factors. This is just the function n squared. And once we get out here into these larger numbers, these really are behaving in the same way. Oops. Okay. And so the way that we formalize that is with big O notation. And so big O notation, it's very formal. In this class, you're not going to be asked to prove a statement like this, but I think, like this statement right here, but I think that it is useful to see how you would prove it. And so I'm going to go through that right now, just to kind of nail down what we're talking about here. So we say that given two functions, so one f of n and another g of n, we say that the function f of n is big O of g of n. So that's how we would say this, big O of g of n, if we have positive constants c and n0 such that these two statements are true. F of n is less than c times g of n for all n greater than or equal to n0. So we're basically saying, like our f of n, an example f of n here would be this 2n plus 10, that we want to characterize this generally. How does 2n plus 10 grow? And what is its asymptotic growth rate? In our claim, when we say that 2n plus 10 is big O of n, is that its asymptotic growth rate is the same as the function n's asymptotic growth rate. So n is g of n. Like the function n is the function g of n in this example. And so if we translate this into, looks like our sizes are probably reasonable. So if we translate this into, what do we actually need to show in order to prove this statement? We need to show that 2n plus 10, right? So that's our f of n, is less than or equal to c times g of n. But what is g of n? Anyone know? What's g of n? Yeah, it's n. Exactly. So this is I've just copied down this exact statement right here, but I've plugged in our f of n and our g of n. So our f of n is 2n plus 10, and our g of n is n. So we need to show, maybe I'll say, need to show that this is true for n greater than n0. So basically, we need to give this c and this n0. And so basically what we can do is start simplifying and see if we can, because like right now I'm not like, oh yeah, it's really popping out to me. Like c should be 100 and n0 should be 10, right? So what we can do is start to manipulate this this statement right here and see if it's going to give us anything where it becomes obvious what a good choice for c and n0 are. So what would I do? Well, I'm just going to work on this up here. So I would say 2n plus 10, so I'm just moving this up here, is less than or equal to cn. Well, I'm going to move cn over, so 2n minus cn plus 10 is less than or equal to 0. So I just subtracted 2n c times n from both sides. I'm going to factor out a 2, so I got 2 times n minus c plus 10 is less than or equal to 0. Then I'm going to move I just want to put these on different sides, so I'm going to put 10 is less than or equal to negative 2 times n minus c. So I just subtracted 2 times n minus c from both sides. But that's just equal to 2 times c minus n, right? I can just distribute that minus 1 into my parentheses. And now, yeah.
When you factored out 2 out of n, 2n minus cn, do you need to factor out n?
Oh yeah, I think I did. I was like, I'm not going to get an n by itself here, am I? So yes. So I should have factored out, yeah, let's go back here. So, yeah, so n could be factored out here, so then I have 2 minus c. Yeah, I was like, this is not looking good. So n times 2 minus c, okay, now I'm going to subtract that from both sides, so I get minus n times 2 minus c. And then I can multiply my minus 1 into the parentheses, right? So I got n times c minus 2 now. And now I'm just going to divide both sides by c minus 2. So I've got 10 over c minus 2 is less than or equal to n. And so this statement, this statement right here is the same as this statement right here, but I've kind of isolated my n a little bit more so that I can see that if I choose c equals 3, then, okay, if c equals 3, then 10 divided by 3 minus 2 is 10, right? So in that case, then the left-hand side is 1, right? No, left-hand side is 10. And so 10 less than or equal to n. So then I have 10 less than or equal to n. So for which n is this statement true?
For all n greater than 10.
Yeah, exactly. If I choose any, this is true for all n greater than 10, and that, gives me a way to choose my n0. Well, that means that n0 can be 10. And so all I needed was one choice of c and one choice of n0 to make this true. But there actually are many, many choices that would have made this true. But so this is how a very detailed proof that a function like 2n plus 10 is big O of n would go, yeah.
With your work in algorithms, does this get harder?
So I think a lot of times you end up having to do tricks like you have functions that are, you can't just subtract things. You have to, a lot of times you're using upper bounds on things. Like you could say, I think even the book even gets into this. If you are doing things randomly, for example, or like you're choosing, if you're doing things randomly, then maybe you say that the example in the book at least is basically you end up with a function that turns out that it's equivalent to the harmonic mean of something. And so then we've gone from kind of sometimes, there are different parts that can be hard. There can be, oftentimes when you're actually down to a function, it's actually pretty easy to show what big O of n it is. But actually figuring out how many primitive operations your algorithm takes can be more complicated. And that's where kind of some knowledge of functions, more kind of classical math knowledge can come in to get you to how many primitive operations is in your function, or does your algorithm do. Cool. But really, the intuitive thing that's going on here is that we have, the intuitive thing is that my blue function here, 2n plus 10, it's possible to move around using just, by moving this n function around just by multiplying it by constants, which moves it up, or by adding, pushing it left and right. It's possible to upper bound the blue by the red just by pushing it left and right. Whereas, in this example, we can never upper bound the blue. We can never upper bound the blue by pushing the red left and right. I push it up here, blue is still greater than red after a certain point to the right. I push it even higher, it's not on the picture, but we would know that the blue function would still exceed the red after that. And so what's happening here, the function n squared is the blue, and we'd say it's not big O of n. So again, this is our f of n is our g of n, and it's because we can never choose an n, we can never choose a c, we can never choose this c and an n0, so that after a certain point, the blue is always less than the red. Is the intuitive intuitive understanding here. Okay, so we're back to our array max, our function that we counted the primitive number of operations. We got 6n, and now we know that this is big O of n, and so we can make statements. Now we can say this algorithm for array max, we would say this algorithm is faster than something like merge sort, which is big O of n log n. And so now we have this way of actually saying, once n gets big enough, then array max will run faster than merge sort. They don't do the same thing, but if we were testing them, there is some point where it's definitely true that array max will be faster than merge sort after some big enough n. Okay, yeah.
So are there ever cases where you choose like the O of n squared function over the O of n because it has better constants for n zero?
Oh, so if I have two algorithms, yeah. I think it's possible. In my experience, not really, but yeah. So it is definitely really important to understand that when we're saying like that this O of n is hiding all the constants and all the lower order terms. And so if you could have something like a one O of n algorithm that is really 6n operations, and then another O of n algorithm that is 2 to the 100 n operations, right? So this, we don't even have to go between classes of algorithms to see that in practice, we would want 6n. That's way faster than 2 to the 100 times n. But asymptotically, there is a point where they're going to grow the same. Like, basically, there is some really big n, really big input size, where these are going to start growing at the same rate. Yeah, I don't have any experiences of actually choosing of the constants turning out to be sort of important, but it could definitely happen. Okay, so I want to go over some big O takeaways. So we say that these primitive operations, we say these run in O of 1 time, or we can also say this is constant time. So if you hear that, that's what that means. And this includes, like we said, if we have an array, indexing into it, also getting fields, etc. Lots of primitive operations. Also, yeah, like we've said, lower order terms and constants don't matter. We just saw that on this slide right here. Another thing that I think is really important to realize, just to make sure that you understand what we're talking about, is big O, this g of n, it doesn't have to be the smallest g of n. So if I have 6n again, we've said this is O of n. Also, another thing, you can say it's the same thing to say 6n equals O of n, and also 6n is O of n. Different people just like saying different things, but they mean the same thing. But anyway, it's also true that 6n is, that 6n is big O of n squared. And does anybody have any thoughts about, how about any justifications for why this would be true in words? I saw a little bit of a hand. You want to go for it?
Maybe it's something like you can't, like, n squared isn't O of n because you can't apply, like, another n to the thing, but you can do something like apply the square root of n squared.
Yeah. So I think the justification, so why is n squared not O of n? And I think you're exactly right. It's that I don't get to shift my function by, say, multiplying it by n. I only get to shift it by multiplying by constants and by only considering an n, like greater n's. But I would say, the reason that 6n is big O of n squared is that, n squared is definitely bigger than n, right? And all this big O notation does is it tells us an upper bound. It doesn't tell us any lower bounds at all. There's a different thing that you'll learn, I'm sure you learned about in 246 and maybe you learned about in 232, but if we want to make statements about lower bounds, we have a different notation. So, yeah, big O only gives us upper bounds. So, yeah, this is definitely true. And it would be true, other examples like log n is big O of 2 to the n. Like anything, these don't have to be tight. And then finally, so we're talking about worst case runtimes. And I think a thing that people get confused about a lot is that while big O does make a lot of sense for measuring worst case runtimes because it gives us an upper bound, it doesn't only apply to worst case runtimes. We can also measure best case runtimes in terms of big O of n, or big O notation. So could also use for best case, for example. That's just one example. So we might have an algorithm that has a worst case runtime of big O of n squared, but a best case runtime of big O of n, and that is a totally reasonable thing to say. There's nothing wrong with saying the best case runtime is big O of n. Okay. Okay, so our papers worked really well last time, so we're going to pair up again, and you can actually turn in your papers this time. But make sure that you write, so just count some papers down. You need to find at least one partner, write your names, pass some papers down. Every group of two or more needs to write out one paper and write down the name of your partner. So find at least one partner and have one partner. And you're going to try to work on this for a couple minutes.
You want last names on these guys?
No, doesn't matter. First names is enough, but I am going to collect them this time. I forgot to do that last time.
So. thought so far?
Yeah, I mean, I've started
Yeah, it's gonna approach some fixed value. So it's gonna kind of get better. It'll take the same amount of time. What's the word after faster? T-man?
Than, yeah.
Than. Thank you. Sorry.
Yeah, my...
All good. I'm also off to the side here. Perfect. Yeah, so I think at best, we just have the log. So for all of the students, yeah, for key numbers next, it's this one. I think I'm going to approach yeah. Yeah, because it can't be faster. So, and I'm assuming that less than but I also, what's the worst case? What if you got some really nasty numbers that take for a long time?
That's what I think. Because I think I started because it's a function
Okay, let's come back together for a second. Okay, all right, listen up. We'll go back into our pairs in a second. But first, so in terms of how do we reason about this? So, I think the first thing we want to do is understand what actually happens in, and I guess I did this in the opposite order of the question, but what would be so now we know, so basically log n is faster than n. So, knowing that, what would be the best case input? What does it look like? All the numbers are odd, exactly. Right? Is that okay? Yeah. Odd numbers do log n, which is faster. So, okay, what's the worst case input? All even, right. Okay, so now I'll give you one more minute to talk in your pairs and think about now what do we think the overall run times are. Well, what did you think it was?
I thought there's an array, like a random array of messengers in this one it's taking like the first one and it's doing a call operation.
Oh.
And then it's taking the second one. The second one is doing a operation.
Oh.
So that's, yeah.
Yeah. Yeah. I understand. Does it make sense now?
Yeah, it's an array of numbers. And the numbers odd, then you'll
Yeah.
Do we have to specify that like one odd number would be the fastest input, or do you just specify all odds as that's?
Yeah. That's a good question.
It seems like one odd number would be faster than
Yeah.
odd numbers. Why is log faster? Because on the graph it seems like it plateaus.
So that's
I mean, what is log?
so like all odd.
Oh, no, it's 2.
Yeah.
Well, if you don't specify the base, the base is 10, so
What is
I'm not getting the end.
n?
I'm getting the end because it has the food log in.
It's 100.
Like it's
The n,
something with the numbers.
if f of n is n, wait, if f of n is n,
then it's just y equals x.
yeah,
How is that faster? Because log, you have to like do some arithmetic rather than y
okay,
equals
faster meaning it's a smaller number.
Like that's what faster means?
Yeah,
That's not faster, that's a small.
So think about what your axes are. Like
Why is it called faster?
well, okay. But we need, okay, we'll come back together and we will solve this and hopefully dispel some confusion, which is good because really our goal in this class is to understand what do we mean how do we measure the runtime of algorithms? What are we talking about when we're talking about the runtime of algorithms? So what we're talking about when we're talking about the runtime of algorithms is we want to consider all possible input sizes. That's why our function, our runtime, is in terms of n. So that by having our functions be in terms of n, the input size, now we're considering all possible input sizes. And so when we think about what is the best case input, it does make a lot of sense to say, well, the best case is only one, like size 1. But I can't really write a function of n by fixing n to be 1. I've got to have, like, the definition of a function is it's defined, well, maybe it's not, but our functions definitely are defined for n equals 1 to n equals infinity. That's the point of our functions, right? These runtimes are of the form f of n, and n needs to go from 0, 1, forever. And so when we say, in this case, what's our best case input, we have to say that it's some input where all the inputs are odd. Like all the values here are odd. We can't just say, it's a length 1 array. Does that start to make some sense? I know it's maybe hard to, yeah. Okay, so we want to define runtimes as a function over all input sizes. Okay, so then there's also the question of how can it be possible, like why would log n be faster than n? And when we say faster, we're saying an algorithm that has runtime log n is asymptotically, we would say that is a faster algorithm than an algorithm that has runtime n. And there we're really talking about evaluating the function log n and evaluating the function n. So for example, if we're base 2, like log base 2 of 64, I don't know, it's something like 2 to the 5th. Yeah, it's 5. But, 64 is what the function n would be when n is 64. and 5 is clearly smaller than 64. Yeah. And really, this was just to kind of make it concrete. What we really care about is the function log n is upper bounded by the function n. Like, the function n is definitely bigger after some point than log n is. And that's why we say that a log n algorithm is faster than an n algorithm. Just like we would say an n squared algorithm is slower than an n algorithm. Okay, so let's think about our best case. So we said in the best case, we're all odd. So can anybody tell me what our best case runtime is in Big O? So we definitely do log n per element. But we're processing, the idea is that for each odd number in X, so if they're all odd, how many odd numbers are in X? N, right. Yeah. So n times the length of this array is n. So there are n elements, and for each one, they're all odd, we have to do a big O of log n thing. And so n times we do big O of log n thing, so our overall runtime would be big O of n log n. Make sense? I think it's hard stuff, yeah.
One question for your first case input, you said that n is 0 to infinity.
Mm-hmm.
Is it -2 in your...
Oh, well, okay, sorry. I'm saying that our runtime, so our goal is to write down is to characterize the runtime.
Is that n how many elements it would be?
And n is the input size. So f of n is the runtime, and it has to be defined, we want functions we have to be able to find these functions for all input sizes. And so I think of all input sizes as, okay, maybe not size 0. Maybe size 0, I don't know, I guess an empty array makes sense, but yeah, maybe size 0 is fine. Yeah. Cool. All right, so now let's think about our runtime for our worst case. You have a thought, but you've answered a lot of, do you have a question?
No,
Do you have an answer? What was that?
I think I know what it is.
Okay, well let's see if anyone else thinks they know what it is. I saw a pen, yeah.
Is it O in squared?
Yeah, and why would you say that? Yeah, so in the worst case, every element is even. And so for every even thing, we're doing an O of n operation. And that's why we get an overall runtime of big O of n squared. Yeah, okay, so that was everything that I wanted to do with big O notation. Really our intro to how do we measure the runtimes of algorithms, how do we compare them. We'll do our, actually, let's see. I'm going to go back. I'll give you, yeah. So just to prepare ourselves for Wednesday, I'll just open this up. And so our goal with, on Wednesday is going to be, again, to make precise, so we've been making precise what is the runtime of an algorithm. our goal on Wednesday is to make precise, what does it mean for an algorithm to be correct? How do we actually prove that it's going to do what we say it's going to do? And so the way that we're going to do that is with something called a loop invariant. And so, for example, here we have a really simple algorithm. It's just going to, the claim, this is our claim, is that this algorithm returns index j such that the input array data has has a value that we pass in at index j, or it'll return -1 if that is not in there. But how do we prove this? And we're going to see that loop invariants are one way that we can do that. So yeah, we will end class there, and I will see you all on Wednesday. Feel free to come up if you have any questions. Oh yeah, I'll take your things. You can see your partnerships. Beautiful. Thank you.
I had a question.
Yeah.
So, did all my programming and stuff. Yeah. I can see,
Weird.
and I couldn't figure out, am I doing something wrong? I add more data points, so you can see I add all these other values before making this graph.
Okay.
And so that was like that giant divot is the weirdness. The other one, perfectly matches up, like just increases that highlighter constant,
Yeah.
right there. But that was super weird. Otherwise it looks...
Also, okay, because I would think that, is this just a regular...
Thank you.
Oh, I'll take that. Yeah. Algorithm 2, I would think should be linear.
I didn't copy paste, I typed and pasted. So, could be me. But both of my graphs, like this did look like it was almost quadratic in nature.
Yeah, like that looks more quadratic.
Yeah.
Looks like there.
And all I did
So
was
like,
add,
you've got 9, okay. Because it should be, it should be algorithm 2.
Okay.
And so you should be having, like if your input is at 100,000,
Yep.
you should have like about 100. Like this should be about 100,000, which would be what, E5 or something.
Mhm.
I don't know. I forget.
You were talking
Scientific.
the bottom one?
Yeah.
7.8 times 10 to the 9.
Yeah. Like shouldn't that be what is times 10 to the 5 is 100,000.
Yeah. 5 zeros. Yeah.
Yeah.
10. Yeah. Five zeros. Yeah.
So I would think that if this algorithm is linear, then it should be something like 10 to the 5. And like, I think I actually have, here. Let me stop this.